Hi everyone. So today we are hosting a very interesting webinar on Introduction to Time Series Modeling, a must-know concept for every data scientist. My name is Deepika Singhal and I am a community manager at Analytics Vidya. I'll be the moderator for the webinar and I'm delighted to introduce Dr. Vikas Agrawal as a speaker for the webinar. So before we start the webinar, there are a couple of important points I'd like to cover. First, we'll be recording this webinar and the recording shall be shared with you in the next couple of days. Secondly, we are also streaming this webinar's Facebook account, so you can join us there as well. Thirdly, there's a chat window and you can ask any questions to us that you might have during the webinar, and we'll try to answer all of them as the webinar progresses. Now, coming over to a speaker, Dr. Vikas Agrawal. He works as a senior principal data scientist in cognitive computing for Oracle Analytics Cloud. His current interests are in automated discovery, adaptive anomaly detection in streaming data, intelligent context-aware systems, and explaining black box model prediction. And he's also a speaker at DataHack Summit. So guys, I'm really excited to share about DataHack Summit, which is the upcoming conference by Analytics Vidya. So this is the third edition of DataHack Summit this year, and the summit is going to be India's largest conference on applied artificial intelligence and machine learning, where we will unleash the era of super AI. Around 1,000 plus AI leaders and top data scientists will come together to unveil latest developments in AI, discuss the challenges and future of AI and ML. The focus areas of this conference will be artificial intelligence, machine learning, deep learning, NLP, quantum computing, and more. We'll be hosting 8+ workshops this year as well. And this is going to be a 4-day mega event. There'll be like 70+ sessions, 30+ hack sessions, 8+ workshops, all by AI leaders and grandmasters. So here's a list of speakers that we have. So there's a gentle reminder. The ticket prices are going up on 1st of October. So make sure you book your tickets early. So Dr. Vikas, can you hear me?
Yes, I can hear you.
Okay. So before we begin the webinar, I would love to know about your experience with DataHack Summit, since you have been a part of this conference since 2017 when we started this. So how has been your experience at DataHack Summit in the past years?
So my experience has been that some of the very best people from the industry and from academia as well attend the DataHack Summit. And even as a speaker, my experience has been fabulous because the kind of questions people ask, the kind of work people are doing, just that atmosphere is amazing. Then the other thing I find is that the content is exceedingly well curated, and the event runs like clockwork. And I know it's not easy to make that happen, having been part of other program committees. The other thing I notice is that the hack sessions and workshops are a highlight for me. I look forward to the hands-on learning. And I noticed that in the main conference, it's a great place to learn about the latest innovations and connect with people doing interesting work. So I personally look forward to this DataHack Summit every year.
Okay, thanks sir for sharing us your experience. So this year, what are we going to learn from you at DataHack Summit? Could you tell us briefly about your talk?
This is a very interesting talk because we've seen a lot of growth from deep learning systems coming in, people thinking that, you know what, we put data in outcome models and we can understand everything. Now, the challenge we see in most enterprise problems is that the purely data-driven machine learning approaches, they work for the leaf level models. But typically the models we tend to create are hundreds of models with a, think of it as a hierarchical pyramid. Now, how do you make so many of these models work together to get a single or a list of recommendations to an end user or a decision maker? How do you give them actionable intelligence? And more what you will see coming in the next year, next 5 years, we'll see more and more of these hybrid systems come in where you have knowledge-driven intelligence systems. So I'm going to talk about these knowledge-driven intelligence systems which use existing domain knowledge and data-driven approaches to give very high quality actionable intelligence for end users. That's what we're going to talk about.
Okay, great, sir. This looks like a really exciting session. So we're all waiting to hear you at the Data Hack Summit 2019. So let's start with the webinar. Over to you, sir.
Thank you. Thank you. Right. So I'm going to share my desktop.
Yeah.
I'm assuming people can see it. Is it visible?
Um,
Okay.
it is,
Now it should
yes.
be visible. It is? Okay. Okay. So I'm going to start with something interesting which has to do with time, very important time series, certain very important time series.
The popular idea of cutting our emissions in half in 10 years only gives us a 50% chance of staying below 1.5 degrees and the risk of setting off irreversible chain reactions beyond human control. 50% may be acceptable to you, but those numbers do not include tipping points, most feedback loops, additional warming hidden by toxic air pollution, or the aspects of equity and climate justice. They also rely on my generation sucking hundreds of billions of tons of your CO2 out of the air with technologies that barely exist told with just business as usual and some technical solutions. With today's emissions levels, that remaining CO2 budget will be entirely gone within less than 8.5 years. There will not be any solutions or plans presented in line with these figures here today, because these numbers are too uncomfortable and you are still not mature enough to tell it like it is. You are failing us.
So notice that Greta is talking about a very interesting time series. Here is the time series. Actually, I'll show you two time series. One is the CO2 time series over time, over years, and another is chlorofluorocarbons, which is the red time series here. Now notice that in the 80s, or actually in the 70s, many countries started taking action on chlorofluorocarbons. And today what we have is that the effect of the chlorofluorocarbons has gone down, whereas the CO2 continues to go up. So there is some merit to these time series models that we're going to talk about. Now, of course, we're not going to talk about models as complex as this one today, but we'll set the stage for some of these. So here we go. My email address is on here. Somebody needs to reach out to me for some specific question later on. All forecasts are wrong in some way or the other. Some forecasts are useful in some ways. So that's going to be our sort of bottom line here. Now let's start talking about what is a time series. Well, what a time series is what happens to any process, industrial process, business process, natural process in the real world. What happens? Well, it takes birth, meaning it's created, it grows. In the process, it gets influenced by other processes. It influences other processes, stays for some time, and dwindles, gives way to new processes. Now, you may say, well, okay, fine, it happens, so why do I care? Well, here's why you care. Because we may want to control the process or plan for eventualities, such as the one that Greta mentioned, that we will not have a world, we will not have a place where we can breathe properly. Right? So we want to control the process or plan for eventualities. We want to look for trends, anomalies, risks, opportunities. So that's the basic idea. We want to monitor the process. So that's one part of it. So that's your detecting what is happening as part of the time series, and being able to make a forecast and say, can I do some preventive control? That's where this basic story comes in. Am I sharing my video? I don't know, maybe that'll help or not. Let's see, sometimes. Okay, my videos, I don't think it will work. So I think we'll keep it this way. I think the bandwidth issues will not be challenged. Okay, so somebody says not able to hear properly. Are people able to hear properly? Deepika, are you able to hear?
Yes, I can hear, sir.
Okay, thank you. Yeah, I think I see some comments from some people. Okay,
Right.
thank you. Right. Now, there is a class of time series called stationary time series. Now there, what we need to do is analyze, and then we can use statistical process control techniques, and we will see for this class of time series what we can do in today's discussion. Now, notice that we may want to control the process or plan for eventualities, but the world changes, its processes change, the time series change. So now, therefore, these forecasts are non-trivial, right? If everything in the world stayed the same, then it really wouldn't matter what you do. Whereas if the world does change, then it does matter what you forecast. So let's look at some examples, right? We already looked at the climate example, right? So time series can occur in interaction of finance, CRM, manufacturing, supply chain, sales, human resources, acoustic and electrical signals from machines. So this is in the Internet of Things space, customer demands, production rates, electricity load and smart grids, traffic and telecom and transportation networks, stock prices, EEGs, ECGs, temperature, other weather signals we talked about. Now, what are the sources of the change in dynamics? The reason I bring this up is to set the scope of this talk. So we will talk about some simple sources of change in the dynamics of a time series. We are going to talk about trends and decays, growth and decays. We are going to talk about seasonality. These are on the left-hand side in this yellow box. And so we'll talk about cycles, seasonality. We will not talk about covariance variation. We'll not talk about periodicity, cyclostationarity. We're not going to talk about skewness, kurtosis. We're not going to talk about piecewise stationarity, arbitrary variation, and so forth. Why? Because we have a certain amount of time. So if you're looking for any of these items, now is the time for you to save your time. We are not going to talk about these items. We're only going to talk about the what's on the left. Also, in terms of the methods or the techniques that we're going to discuss today, here is the list. Right? We are not going to talk about exponential smoothing. We could have talked about it, but we may not have time. We will talk about ARIMA methods, which is autoregressive, integrative, moving average methods or extensions. We could have talked about vector autoregressive methods. We'll not talk about them. We'll not talk about vector error correction methods. We'll not talk about GARCH. Each of these is very, very interesting. However, given the time, usually this would be a full day course if we were to cover many of these items. Right? And for some of these people have gotten Nobel Prizes. We are not going to be able to talk about LSTMs, which is a very, very interesting area in time series modeling. We're not going to be able to talk about time frequency domain methods like wavelets or Fourier transforms. We are not going to be able to talk about particle filtering or Markov methods, Dirichlet processes, and so forth. So we will talk, so in summary, we will only talk about univariate models of time series. The multivariate models are a lot more fun, but I think these form, the univariate methods form kind of the basic understanding of how time series works. So we will talk about these seasonal autoregressive integrated moving average models. These models assume that the variance of the error does not depend on the value of the variable, as in it just doesn't blow up. Now, what we'll not talk about, another list, I will not talk about causal models, temporal causal models, which are even more interesting. We will not talk about co-integration, which is part of the temporal causal models. We will not talk about lots of sources of non-stationarity, although we'll talk about non-stationarity. And let's see, we are not going to be able to talk about dynamic mathematical models supported by these models. If you want to hear about these dynamic mathematical models, please come to the Data Hack Summit, this last part, and some of these other ones. If you come to the Data Hack Summit, my talk will include this material, the last one. So these we'll not talk about today. So this will be, in short, an introductory talk to time series modeling. So let's get going. Talk about nonlinear dynamics, aperiodicity, asymmetric cycles, multimodality, nonlinear relationships. These are all good areas of work, things that I work on day to day. But today we will not have time to get into these. perhaps at the Data Hack conference, there will be some of these topics addressed. Okay, so there's a quick question. How can I get to know about what we'll not talk about list? So one part is Analytics Vidya is a very beautiful website where some of these topics are addressed. But usually the best place to get information about each of these topics is, one, to take a full course in these topics. And I think there will be workshops at the Data Hack conference. Surely there are online courses. And if you're interested in a particular topic, I can share with you, specific information. In particular, if you're worried about non-stationary time series or your work involves that, I'll be happy to share with you. Okay, so these will be discussed another day, the topics that I mentioned here. Okay. Now, that doesn't mean we won't have fun today. We'll have a lot more fun today. All right. Now, in time series, you could have different kinds of changes, right? You could have trends, right? Which is, here what we are showing is a linear change, but this might as well be a quadratic change, right? As something as simple, as trivial as v is equal to u plus at, s is equal to ut plus half at square. Literally that simple, right? And this can be modeled, right? If you differentiate, so let's say you get this data, the time series data, right? Now, a lot of these models have come out of the world of the econometrics. However, if you look at the methods they use, they call differencing. In standard mathematics, that's just differentiation, right? You can just say what is dx by dt, or you can say what is d2x by dt2, right? So first derivative, second derivative, and using that you can make any system stationary or non-moving. So we'll come to that. Also, we'll talk about seasonality. This is again coming out of econometrics. The terminology is coming out of econometrics, where they talk about seasons if there is an annual sort of variation in items, right? So if you have something that recurs in January, or if something that recurs around Thanksgiving, those kinds of items come under seasonality. Again, these can be addressed by saying, you know what, my current value depends on a value 12 months ago, something like that. Right? And then, of course, in the real world, you will have trend plus seasonality, right? So you can see there's a downward trend here, which could be modeled using one of those differences that I mentioned. And then you have the the seasonality, which can be modeled using 12-month or 3 months or 6 months prior periods. Again, the months comes from econometrics. For your particular domain, let's say you're monitoring an electrical motor, the frequency may be very, very different in terms of what you consider seasonal for your monitoring. So we mentioned this important term to learn about time series, which is called stationarity. Now, what is stationarity? Okay. Now, stationarity, strictly speaking, is if your time series has a constant mean and a constant variance, as in your time series keeps coming back to the same value over time, it doesn't deviate from there, and it stays within a certain bound of variance. If you look at the time series on the left, which is the green one, it stays within a certain bound and it keeps coming back. It doesn't just drift off. Whereas the one in the middle, right, the variance keeps changing. It keeps increasing, then it is decreasing. And in the third one, you see there is a trend. Of course, we can address that one. Right? Now, why do we care about stationarity in time series forecasting? Very simple, because that lets us use simpler models. It's for the same reason in physics or in chemistry, you assume quasi-stationary states or quasi-static states. There's a question, if the data is stationary, can we only use simple average means? We'll address that when we look at the actual data and see how much average gets you. If you just use average, the challenge is very simple, right? If you use an average, you just get one value, right? So that will be your prediction, and that may not be, like if you look at this sine wave kind of thing, the average will not cut it. Well, then you may say I'll use a moving average, so that will be an improvement. So like that, we can improve the system. Yes, so we can keep adding terms. Now, it's an interesting question. What is the difference between forecasting and prediction? Which one is better? You tell me what is the difference. Honestly, I don't know the difference, because literally they mean the same thing, at least dictionary meaning wise. Forecasting came out of the econometrics world. The word prediction came out of the statistics world. So now it's basically the same thing. Okay? Now, how about smoothing for stationary data? Yes, we'll talk about that. Okay. Now, what is stationarity? Again, we said that the distribution is invariant to shifting in time. As in, you look at the distribution here, you look at the distribution to the right side, and you get the same mean, you get the same variance. Okay? Now, here is some practical view of the stationarity issue. Now, so there's this strict stationarity. Strict stationarity is that any moments, first moment, second moment, third moment, which is, mean, standard deviation, or variance, skew, kurtosis, all of those are non-changing. Now, in practice, this definition is way too strict. Practically no process follows this. No real-world process follows this. Now, first-order stationarity series, they have means that don't change with time, but variance changes with time. So this is something we can address. This is somebody got a Nobel Prize for addressing this one. We will not address this one today, but we will address the second-order stationarity, which is also called weak stationarity, where the time series have constant mean and variance, and an autocovariance that doesn't change with time. Now, other statistics can change, but the variance doesn't change. So that's very important. And here are the examples. So what you'll notice is that basically the series keeps coming back to the same mean, and it stays within a certain range. That's basically your weakly stationarity, intuitively speaking. Okay, so Jay has asked any industry example of stationarity. In fact, I was going to come to that. If you hold on to that question, I will address that. If you hold on to that question, I'll address industrial examples. Inputs about compound. Okay, so the question about inputs about compound seasonality, how to handle with SARIMAX. Compound seasonality has to be handled separately. We will not cover it today, but we can talk about it. Perhaps if you come at the Data Hack Summit, we can talk, sit down for half an hour and talk about it. That is also the story, what is called cyclostationarity, where you are really dealing with two time series working together. But we'll not get into that today. Okay, oops. So this is your weak stationarity. Let me just skip this, we talked about it. Now the second type here is the trend stationarity. Series which fluctuate around a deterministic trend. We talked about this. So you look at this trend here. Now these trends can be linear, quadratic, cubic. And the important thing is that the amplitude of the fluctuations neither increases or decreases across the series. So that refers to the variance across the series. You use a KPSS test, which we will briefly address, but we will refer you to the Analytics Vidya website article on this one. If the data contains outlier, is the average the way to go? We'll address this question later on. Simple response is outliers have to be addressed. You cannot just average them out. All right. Now, the good thing about the trend stationary series, they're also called difference stationary, which is that if you difference out the series, as in you take the whole series and you difference one shifted series, essentially taking a derivative of the series, what you might get is a stationary series, as in this case, right? So you have this series which is red on the left, and then you difference out single difference. So this is nearly linear. So if you do a single derivative, you will get a constant, which is what you have here, right? So like a y is equal to mx plus c kind of, or y is equal to mpy plus c kind of scenario. Right? Now, on the other hand, if this was a quadratic one, right, if this trend was a quadratic one, then you would have to probably difference it twice. Right? Now, once you've done that differencing, then you run the Dickey-Fuller test or KPSS test, which we will do at a little bit later point in time in this discussion. Okay, cyclostationarity we will not discuss, but there was a question on this, so I'll just address that right here, that cyclostationarity is really equivalent to 2 or more interleaved seasonal processes. So those have to be handled in that way. Okay, now I'm going to address this question about where do you find stationary time series in industry. Well, so my claim is, and it's a very strong claim, that one cannot find a real world process which is stationary left to itself. Now, if you have found one, let me know, because then you have found an exception to the second law of thermodynamics. Or you're looking at the process over a relatively short period of time. Now, if we can't, we are stuck dealing with non-stationary processes. Now, where are the processes which are stationary? Only carefully controlled and maintained processes are stationary. For example, I used to work at Intel Corporation. The fab processes at Intel Corporation are very tightly controlled. They have this 6 sigma limits within which every single machine has to, all the parameters of each machine have to lie, and also of the product. So in short, only very properly controlled processes are stationary. Now, there is a good thing about that, which is that given that they are stationary, now you can figure out how to keep them that way through a control system, which is what we talked about. Why are we doing this? We are doing this so that we take those the processes we can control, come back and continue to control them in such a way that they remain stationary and they don't blow out of control. Okay. Now, there is one more claim I would like to make, that we are going to talk about univariate time series here. My claim is that there is no physical process in the world which depends only on itself. So therefore, some of these methods are kind of useful for very simple processes, but once you get to true industrial process, because somebody asked about the true industrial processes, what you have to worry about is how many other processes my current process depends on. Because what might happen is that the stationary processes are giving you the illusion of being predictable from their previous states, simply because there's a controlling and maintaining mechanism, and perhaps there is another variable or another 5 variables which are making it appear stationary or non-stationary, which means that the relationship between variables have to be examined. Now, in today's discussion, we'll not get into that. We will talk about univariate, we take step by step. So we'll go there. Okay. So, okay, now you might say, all right, I need a model to do some forecasting, or as somebody said, prediction. Now, what is a model? Everybody knows this, right? So if I'm going to predict a y at a horizon, so horizon means, few time points out from the current, what do I need to do? I need a function of the current, and whatever current information I have, I need to create a function of that. So, and either it could be linear or non-linear function, but basically it could be all the y's I have seen before. So it's yt minus 1, t minus 2, up to y1. So these are the time points. The t's are the time points, and it could also depend on exogenous variables, meaning other variables, which are here represented by a vector of x's, xt, xt minus 1. Now, in today's discussion, we'll not get into the xt's, but this is a very interesting area of research, a very powerful area of research, which can help us solve many problems in the enterprise. We can come into that when there is a time for questions. So we already discussed this part. Now, you can have a model as simple as a very naive model. right? You could say the forecast for tomorrow is basically the same as the value we observed today, right? Very naive, right? Okay. You could make, but then you could make that function a little bit more complex, right? You could say that my model is that I'm going to take a weighted sum, not average, weighted sum of one or more previous steps. Okay? Now, so this is called an auto-regressive model, as in you are regressing on yourself, right? I'm assuming people understand what is a linear regression, right? So what are we doing here? We are essentially not exactly doing a linear regression because the cost functions are different here, but what we are saying is that my current y is a summation of previous weighted y's, weighted by these ai's, right? Y t minus I, right? So up to p. So there might be as many as p previous y's. So the p stands for previous y's, which my current y depends on, right? So this is the assumption I'm making. Now notice, for this to work, we'll come to a test which is required for this to work. But in short, these A's cannot be too large. If they're too large, the process blows up, as in it's not a stationary process. So then these assumptions, meaning the math doesn't work out. In short, you cannot converge the model. You cannot fit the model. So these are the autoregressive models. Here is an example, and I think I have this in my. How do I? Okay, I have this right here. Is this the one? Yeah. Okay. Yeah, let me get started on this one, because if we don't start on this, we will never start on this, right? Now, I'm assuming people understand some of Python. If you are not familiar with Python, it's perfectly fine. Python is not that hard. What we're doing here is we are reading a time series, AR_passengers.csv. Now, if you want to read more details, I've on purpose chosen this very simple example. This very simple example is also found on this link that was shared with you previously. Probably not this one. Sorry, apologies. This one. This is there's an article on Analytics Vidya website on the same topic, and the Python notebook that I have here is the exact same code. Okay? So if you want to read the description of this in the background at some point, you're most welcome to read that, right? But okay, so what do we do? Okay. Here, what are we doing? We are reading the CSV file using the pandas function read CSV. We can look at the header using the data.head, right? We can see what are the data types here. We have number of passengers, and we have the month, right? 1949 January, 1949 February. So basically, number of passengers flying in my airline, right? And what do I want to predict? What will happen the next month, or what will happen the next year? That's what I want to find out, right? So that's just the IO, right? Now I'm going to skip some of this because this is simply IO and just looking at what's in the data. But this is how your data looks like. Okay. All right. So now we come to something interesting, right? Now somebody mentioned, why can't we use just a mean? Now we're not even using a mean here. We are using a rolling average, right? So now notice, so this is the actual time series. On the x-axis you have years, which is the time. On y-axis you have the number of passengers flying, and you will notice that this thing is growing quite fast. But you see there is clearly a seasonal element here, and there is a trend element here. Right? Now notice, if you just do a rolling average, or what is also called a moving average, you lose out a lot of detail. If you just use that as the predictor, you lose out a lot of detail, right? So you need something better than that. But notice here the standard deviation is changing a little bit, but not too much. So this is a good candidate in terms of what kind of what we could do with this time series. Okay, so now one of the interesting things this Dickey-Fuller test does. Okay, let me not get to this Dickey-Fuller test. Let me just show you one more thing here. Now I'm just going to skip this one. Yes. Okay. So what we have done here in this one, right? What we have done is we have subtracted out the moving average, right? Which is essentially your trend. Right? This moving average shows the trend. This is the moving average. If I subtract this out from this series, what I get is a constant mean, right? This is not a growing mean anymore. This is a constant mean. And all you're left with is the seasonal variations, essentially. You see this? There's the seasonal travel variations that are left, right? And your mean has become flattened also. Okay. Okay. So let's see. I'm going to skip this part. You can read about that in the article, but I'm going to skip this part because I want to get to our models. So, okay, yeah, this is an important one also. This seasonal decomposition here, right? What we can do for our time series here is look at a seasonal decomposition to say, okay, there is a trend, there is a seasonal component to it, and then there is what remains, which is the residuals, which is expected to be essentially noise, right? If there is some systematic effect there, then that has to be modeled by us. Otherwise, our model doesn't, our model will have large error. Okay, so now while we're looking at this, let's come back to what we were saying here. We talked about this auto regression model, which is saying that the next step is a weighted sum of one or more previous steps. And it doesn't have to be an immediately previous step. It could be 12 steps back, right? And if you think about that, if you do the 12-step version, that is a seasonal version, right? If in terms of traditional seasons, if I say my value of today is kind of a weighted average of previous seasons, which may be 12 months back from now, that is also an autoregressive model, which is just looking at 12 steps back. Okay. Then there is this other kind, which is the moving average of the noise term, which is, so what you're saying is that your noise is, you're not going to let your noise grow. Oh, no, let me take that back. Sorry. So what happens in this model, right? You have this noise term. Now this noise term is also called a shock term. Let's say there is an external shock to the system. Now what will happen in this autoregressive model is that as long as the process is stationary, it is going to keep overwhelming the shock terms and over a period of time bring it to zero. The effect of it, the old shock terms are going to be brought to zero. Whereas with this moving average one, you quickly bring it to zero, very quickly bring it to zero. So this is that model here. Now notice, you will see that these don't look very different, right? And the reason they don't look very different is because both of them are second order. And if you think about the moving average of noise, when we're talking about noise, this is actually the difference from what is predicted to the actual, right? So essentially, this includes your Y, and therefore this looks like a moving average. In effect, it looks like a moving average here, right? Now you can combine those, right? You can combine those and you can have an autoregressive moving average model where you combine both, right? You have the previous Ys and the previous noise, weighted average of previous noise and previous Ys. Now, but notice that that's not enough, because some time series also have a trend, which we have not taken care of here, right? So to do that, one has to include this integration. So the idea of integration is literally the same thing that I mentioned about V is equal to U plus AT or S is equal to UT plus half AT square, that you have a linear or quadratic or cubic term. So there are some questions. I may not be able to address it right now. We'll see if we can address it a little later. By the way, the moving average of error, yes, it can be called as lag. That's right. Okay, so now this is an autoregressive integrative moving average model where you have the autoregression, which is the long-term filter. You have the stochastic trend, which could be linear, quadratic, and the shock or error term. And so once you get through these filters, you just are left with the white noise, and that's what our model should be doing. Now, the way these ARIMA models are specified, and I think I mentioned, are using this terminology called P, D, and Q, which I think we mentioned these briefly before, but the idea is the P refers to the AR filter, the D refers to the integration filter, how many times you difference the series, and Q refers to the moving average filter. So now notice what's happening here. So when we say it's a ARIMA 201 process, what are we saying? We are saying that it depends on two previous terms, so yt minus 1 and yt minus 2. There is no differencing required, so there's no trend essentially. There's no trend, and there is one previous error term or shock term. Right? Similarly, for ARIMA 301, you have 3 previous y's and 1 MA moving average and 0 trend. Then you have ARIMA 110. Again, these are not canonical processes. Your process may be, so we'll get into how you determine what this process has to be. So ARIMA 110 is, it depends on the previous term and one level of differencing. So that one level of differencing that we're talking about is this delta yt minus 1. Okay. Similarly, so the delta yt, of course, is yt minus t minus 1. Similarly, you can do a 210 where you have delta yt minus 1, delta yt minus 2. So this is two previous differences. It depends on two previous differences, which is, sorry, not two previous differences. It depends on two previous terms, and your series has been differenced once. So now to build a time series model using ARIMA, this is not the issue, is using ARIMA, we need to study the time series and identify these P, D, Q terms. Okay. So, and here's what that looks like, in practice. In fact, this is what we have in our actual model here. So if we, okay, now how do you determine this, right? How do you determine what number should I use for my, for example, for my moving average, right? Now this is done using what is called an autocorrelation function. So before I get into this unit root, I'll get into the autocorrelation function, which is very interesting. So what is the autocorrelation function? Okay. Autocorrelation function order 1 or lag 1 is you take the series, shift it by 1, right? So yt minus 1, right? And you say, how far am I from the mean? How far am I from the mean? How far is yt from the mean? How far is yt minus 1 from the mean? And divide that by the yt minus y square sigma. Okay. So now notice, what is this telling you? It is telling you how similar am I to a previous series, right? Previous sequence. Now, so one can calculate this. We have a sample calculation here, but we are already at 8:46, so we'll run out of time before we get to our actual to the code. So let me just show you that if you want to calculate higher order correlations, which is if you have a lag of k, right? Then you do the same thing for, we did it for, 1 lag, we could do it for k lag, right? Now, when you do that calculation, you can actually make a plot like so. Right? So let me show you a plot here. Right? Now, so this is the think of the autocorrelation function as trying to create a derivative of my current time series with respect to a previous state of the time series, to say how much does my current time series depend on the previous time series, right? Now, what that will do is it'll give you a full derivative, which is the left hand side. This is the full derivative, which is called the autocorrelation function. Now, this partial autocorrelation function is a very interesting one, right? If you want to do a partial derivative with respect to the only the kth element of the series and nothing else, kth time shift of the series and not all the structure in between, then you do this partial. So this is like a partial derivative, right? So now there's something interesting about this partial derivatives. Notice this, on the x-axis you have the number of time shifts, and on the y-axis you have what is the amount of correlation, right? Now, and these blue lines, the dotted blue lines, are the 5% significance limit, p, p is equal to 0.5, 95% confidence intervals, right? So now, so for one shift you have a high value of autocorrelation, and for the second one you have a high level of autocorrelation, and after that it just falls off. Now, what this tells you in this, the partial autocorrelation tells you, is that this is a moving average process of second order. Now, I wish I could take you through the math. That would have been very, very nice. But given the time, I'll try to do as much as I can here. Now, similarly, if you look at the autocorrelation function, there, if you see, so for example, you have a high correlation with the first shift and the second shift, and then it drops off. So then you know that this is the autoregressive process of the second order. And then you can put those values in there, right? When we said ARIMA 2, 0, 1, right? So in this case, if this is the same process, right, then you would say this is 202. This is a 202 process, right? We haven't talked about differencing yet. Right? Okay, so now let's go back to our code here. Okay. So notice what's happening in the code here. Let's see. On the x-axis, you are going from 0 to 20, and here's the correlation. Right? Now notice that where is the peak here? The peak here is at 12. You notice this? So the peak here is at 12. Now what does that mean? Just like we saw the peak previously, right? So that means that my autoregression has to occur with 12, right? Everything else is below the level of significance. All other numbers are below the level of significance, right? They're outside the confidence intervals. Only this one is higher. So that is why we choose 12 for our autoregression, right? Now, the interesting thing is, so this is autocorrelation function. Now, when I look at the partial autocorrelation function, which we saw, we could determine the moving averages from there. Notice here that at 12, this also shows a peak. So even for moving average, we'll have to pick a 12, right? So what we are going to do is we are going to have a time shifted series of 12, sorry, not, an autoregression of 12 and a moving average over 12 time points, over 12 time points. Okay. So, and that's literally what you see here. Right, so you create a ARIMA model, and we literally specify the order here 2, 1, 0. Now in this case, I have not shown you the differencing. We did a differencing step up ahead, but we are at 8:50, so I have to be careful with time here. Now you take that, and now you see you take the prediction which is in red, and the blue is the original, and you can see that there is some similarity here, much better than just taking a moving average. Right? Now you can also take just the moving average, right? Notice the first term here, the 2 refers to the P of the autoregression. The 0 here refers to the moving average. So this is the regressive process only. Sorry, autoregressive and integrated. right? Now this one is autoregressive. Sorry, this is no autoregressive, only one difference and 2 steps moving average. Right? And you'll see there is some similarity here, and this is very interesting because what you're doing is either you're taking an average of 2 steps, or you are creating a model of 2 previous time steps. Essentially, when you do the fitting, it'll come out with some kind of an average, right? So that's kind of, so that is something one has to work through. Right? Now you can combine both of those. Right? You can combine both of those, and right here, right? And you can get a 2-1-2 model, which is this model, and you can see this 2-1-2 model is kind of following the entire flow. Now notice that there is still a gap here because I have not put a seasonal term here, right? So once I put the seasonal term here, this is going to improve even further. Sorry, let me take that back. I have put in one part of the seasonal term here, which is the 12. Right? Now, if I put in further terms, right, which represent some of these peaks from the autocorrelation function, then I'll be able to get further accuracy in this model and so forth. Okay, so I have covered this basic material. Now, in the presentation I have here, which eventually could be posted, you have the list of tests that could be done and so forth. And there are other extensions which you can read up on. The seasonal components, the ARIMA model, the models with side information. Remember those big X's. There's also fractional integral model which have long memory, which we will not talk about yet. And then how do you select techniques? Somebody had a question about how do you select techniques. Here's a little table for you. But again, you have to apply the technique for you to figure out, right, as to what applies for you. Okay, and with that, I'll stop for any questions. Let me look at, if there, yes. So one question is, will the PPT be shared? My answer is yes. And I think the video will also be shared as far as I know. Now, okay, so there's another question. Instead of finding P and Q values from the graphs, can you find it automatically? Yes, you can find it automatically. You just have to, you don't need to plot it, right? You can just take the function and say all the values which exceed the boundaries, pick those, right? So yes, it can be done without, without looking, without looking at the picture. Let's see what other questions are there. Could you please suggest some other modeling methods which are simple and very useful? For time series, I think this is the simplest possible. Everything else is more complex. For example, I mentioned the G-arch process, right, where you are modeling not just the mean, you're modeling the variance, the change in variance rather, right? So I think let me stop there, and then we'll go further. So what do you say that from ACF and PACF, are you saying that P is equal to 12 and Q is equal to 12? So, okay, let me go back to this one. Okay, no, actually there are 2 things here, right? And I missed one item here, right? One is, actually I missed 2 things, right? So one is this item, this here, right? Where I am just falling below the level of significance, right? So that is where my 2 is. That's where my 2 comes from, right? And similarly here, yeah, I should have explained this, right? So if you look at this partial autocorrelation, as soon as I fall below this level of significance, so just before I fall, that's my last level of significance. So that's approximately at 2 here. That's why we picked the ARIMA models for that. Now, if we took the 12 seasonality, so I was referring to the seasonality there, then, so I just wanted to clarify. So previously I mentioned, right, that I'm going to take the moving average for here, right, this one, for 12. So that was for the moving average, that wasn't for the function. I should have mentioned, it is for the 2 that is coming here for the P and the Q, that comes from before you fall below the level of significance, you take the last value here, which is 2 in this case. And I think in both cases is 2, one of which goes into the moving average and the other goes into the AR. Okay, so I think we're going to, let me see if there are any, okay, for multivariable time series. Okay, so for multivariable time series, there are multiple methods available. And one is, please come to my talk at the Data Hack Conference, but I'll show you the Varimax models here. Okay, so one is the multivariate time series modeling with VAR models, right? So vector autoregressive model, right? This is a vector autoregressive model. And let's see what else. And also there are long short-term memory, for with variable attention and temporal attention. One can use that with multivariate methods. And also somebody asked about the causal systems. One can use temporal causal models which have been developed over time to deal with this. So let me see. So see, in the real world, the systems look like this. Nothing like the simple system we discussed. The systems actually look like this. So now, what do you do with these, right? You have to actually, so this is the kind of thing I'm going to talk about in the Data Hack Conference. How do you do this? The way to do this is you actually create a dynamical model, or delay differential equation based model and a deep learning based model, and then use those to correct each other. That's the typical method for very, very complex systems. Okay, now there's a question, PACF gives the Q, ACF gives the P. I have a table for that here. What gives what? Right here. So this is on slide 53. So for the ARP scheme, the ACF will tail off as a damped wave pattern, right? And on the PACFs, you will get P spikes. So so those spikes tells you that this is the P, right? For the MAQ scheme, you will get Q spikes on the ACF, and PACF will tail off. Right? Now in the mixed ARMA scheme, it gets a little bit more fun because you have to separate those out. Okay. Okay. In ARIMA, we have PDQ and capital P, capital D, capital Q, seasonal and non-seasonal components. Yes, I wish I had the time to explain those. Can you briefly explain the seasonal and non-seasonal component? I think we'll have to end. I think we are at our time limit at this point. So, but I will be happy to, if you come at the Data Hack Conference, I'll be happy to discuss any of these topics further with you. Thank you. So, Deepika, you there?
Thanks, Vikas. Thanks a lot. Thank you, guys. Thanks for attending this webinar. We'll be sharing the recording in a few days. Hope to see you again.
Yeah. Also, I will highlight that please do look at the 2 articles I mentioned on analytics Vidya. Those will be very useful because we had to go through this material very, very fast. So certain things we simply didn't have the time to explain. So I think if you look at the articles, those are good. Thank you very much.